In section 6.3, we're going to talk about normal distributions, but not necessarily standard normal distributions. So what that means is we will not have the luxury that the mean is already 0 and the standard deviation is not already 1. So we're going to talk about what kind of transformations we need to do so that we can use a standard normal table. Now, the thing that we're going to deal with is the z-score formula. We take our score minus the mean of the population divided by the standard deviation of the population. So in other words, we're changing our distance from the mean into standard deviation units. And you round z-scores to 2 decimal places because of how table A2 reads, and z-scores are also known as standard scores. So this formula can be thought of the standardization formula. So if we take a non-standard normal distribution, we transform it using the z-score formula, it goes right into the standard normal distribution. Now let's think about this. Before the world of technology, we have one standard normal table. You have it in your book, you have it on your yellow sheet, it's 2 pages. Imagine that if we had every possible combination of mean and standard deviation, we would have rooms and rooms and rooms and rooms and rooms full of books of tables. So we needed to be able to take any normal distribution and standardize it so that we could use that one table. Now, how do we use this? Well, in this scenario, we have Eleanor who took the SAT math test and she scored 680 on it. And that score has a normal distribution with a mean of 516 and a standard deviation of 114. Where Gerald scored 27 on the ACT math test, and ACT also has a normal distribution, but its mean is 20.6 and its standard deviation is 5.0. These distributions are so different. How can we compare these scores? How can we answer the question, who scored better? Well, the way we're going to answer this question is we are going to standardize both scores. We're going to look at them on where they are in that probability curve, in that density curve. So we're going to standardize each score, and then we're going to compare the number of standard deviation units above the mean, and we have our data up here in the corner. And so Eleanor's standard score is 1.44. So Eleanor scored 1.44 standard deviation units above the mean for that SAT test, while Gerald scored above the mean, but he only scored 1.28 standard deviation units above the mean. So which score is better? Well, the score that's farther from the mean is better. And we can look at this on this picture that Eleanor scored out here. Gerald was just a little bit closer to the mean, so even though they both scored well above the mean for their exams, Eleanor did score higher above the mean than Gerald did. So in this case, Eleanor scored better. Now let's look at another example. Water taxi passengers. It's been determined that a safe load for a water taxi is 3,500 pounds. And that is for the number of people where we're assuming that a mean human being weighs 140 pounds. So 3,500 divided by 140, that means 25 people, mean of 140 pounds. But what if all the passengers were men? And men have, the weights of men have a normal distribution with a mean of 172 and a standard deviation of 29. How are we going to calculate the probability that the passengers weigh less than 174 pounds. So what we're going to do is we're going to take our score, 174. We're going to subtract the mean and divide by the standard deviation. So we get a standard score of 0.07. So here you can see the sketch. You see the mean, you see the weight that we're interested in, and you can see how it's been standardized with a z-scale. You can see that our weight of 174 is slightly above the mean, and the area to the left of it is 52.79, which translates that the probability that one person will weigh 174 or less is going to be about 53%. Now, when you're doing this, some helpful hints. First of all, as I said in the last lecture, don't confuse z-scores and area. Z-scores are the distances along the horizontal scale, but the areas are the regions under the normal curve. The areas give us the probability. The areas are found in the body of the table, and the z-scores are on the left and top margins. Always choose the correct side of the graph. Are we looking at less than? Then we're going to be looking at the left side. If we're looking at greater than, then we're going to be looking at the right side. And then whenever our score is below the mean, then we need to have a negative z-score. And our areas are also our probabilities, and they're always positive or 0, but they can never be negative. And here's some directions that go ahead and follow these. I know you can use these. These are if you're going to use the table. And at the end of the section, since it's so short, I will be doing all the stat crunch at once. Now, if you're going to be using the table and you want to find the z-score when you know the probability, you have to unstandardize that z-score. So what this formula is right here in black, that is the unstandardizing formula, and it's simply an algebraic manipulation of the standardizing formula. So if you take your standard score times the standard deviation and add it to the mean, you will get your raw score, the score that fits in the original distribution. And again, if you have a sketch that helps you verify that your solution makes sense. Now let's look at this, and we're going to use the same data, the weight data, where the mean was 172 and the standard deviation was 29. And it says use the data from the previous example to determine what weight separates the lightest 99.5% from the heaviest. So what we're going to do if we're going to use the table is we're going to search the table for 0.9950. And because that is bigger than 0.5, I know it's going to be on the positive page. I know it's going to be, well, the lower left part of the table. I'm going to search for 0.995. The closest I can get is between 2.57 and 2.58. It's halfway in between. So that's where they got the 2.575 z-score. So now we need to unstandardize that 2.575. So we're going to take that times our standard deviation value, add it to the mean, and we get a score. So rounded to the nearest whole pound, 247 pounds separates the lightest the heaviest 0.5% from the lightest 99.5%. So What do you want to find? You want to find the value of x from a known probability. This is the backwards table A calculations. I want to find a probability from a known value of x. This is what we learned how to do first. So are we going to use table A2 or are we going to use technology? Well, let's follow the A2 first. And so the first thing I need to do is I need to standardize my score, and then I'm going to look that up in table A2. If I'm going to use technology, I go directly to finding the probability by using the technology. Stat Crunch to do this, you go to Stat Calculators Normal. Now, if you want to find the score from the known probability, if you're going to use table A2, then you're going to look up the area of the curve that's left to the left of our corresponding z-score. You find the z-score and then you unstandardize it. If you're going to use technology, then you find x directly from the technology, and that's Stat Crunch. Go to Stat Calculators Normal. Okay, let's look and see how we do those same problems using Stat Crunch. So I've already opened up a blank table, and I'm simply going to go to Stat Calculators and Normal, and then I'll move my normal calculator back into your field of vision. So our first one was to look at the weights of water taxi passengers, and remember we were assuming 25 passengers, each weighing 140 pounds on average for a safe load of 3,500 pounds. But what if all the passengers were men? And that's what we're looking at there. Is we're looking at a normal distribution where the mean is 172 and the standard deviation is 29. And you can see I can deal with any distribution here. It doesn't have to be a standard normal distribution. And I want, what's the probability that x is less than, and I already have less than 174 pounds. And I simply click compute, and there I have the same answer that I got off of table A2. And right there you can see I'm just slightly above the mean. You can click on the 68, 95, 99.7 ticks if you want to, so that you know your standard deviation units. But again, I can quickly find the same answer. So the probability that a single passenger will weigh 174 pounds or less is about 53% of the time. Now let's look at the lightest and heaviest. So I want to look at the lightest and heaviest, so I want to make my x, let's do greater than, and let me make my probability as 0.5%, which would be 0.005 as my probability, and I'm going to click compute, and that's going to be 246.69 pounds, which is exactly, pretty darn close to what they got, and rounded to the nearest pound, it's exactly the same. So the weight of 247 pounds separates the lightest 0.5% from the heaviest 99.5%. Now we could have also done that as finding a z-score. So if the problem said what is the z-score, we're simply going to change our mean to 0, our standard deviation to 1. That's our standard normal distribution. We're going to get rid of that value for the x, keep it at 0.005%, and you can see that our z-score is 2.575, which is exactly what we found on table A2. And then again, we know the z-score, and so when it's 0 and 1 for the mean and the standard deviation, this actually should be a z-score rather than x, when because it's standardized. When it is not 0 and 1, then this x is very, very appropriate. So when we want to know the percent with the table, we would look up the area inside the body of the table and go out to the z-scores. With this, we keep the value of our x empty and we put in whatever area we need. And the nice thing about the technology is you can set it to be greater than or less than. You don't have to mess with the 1 minus this and the 1 minus that. So what we've done is we've talked about how we deal with non-standard but still normal distributions. We talked about how we take those distributions and convert them to a standard normal distribution using the z-score formula. We talked about how we find those values using the table and the formula, and we looked at how we use StatCrunch for those calculations also. So that's the end of our section 6.3 lecture.